All right, today we are going to be talking about waves, and this is going to be chapter 11 in your textbook, and we're going to focus just on intensity and wave properties for today. Let's start off with the definition of a wave. When I think about a wave, I think about an energy transfer from one point to another. And it's not necessarily going to cause a transfer in matter, but just the transfer of the energy. So let's look at an example. If I look at a PhET simulation here, this is one of my favorite PhET simulations, and I cause a wave to be created. Let's turn the damping down. And I create a wave. What we see is just the energy from the wave is traveling left and right, but the particles themselves, the little dots, are staying in place. The dots are not traveling from left to right. They are simply moving up and down as a result of that energy movement from one side to another. So we can really see that transfer of energy without that transfer of the matter. So now we can actually calculate the intensity of a wave, whether it's a sound wave or a light wave or some other type of electromagnetic wave, like maybe a microwave or a radio wave. We can calculate the intensity by considering the power divided by the area. This symbol for intensity is a capital I, and the units for intensity are going to be watts over meters squared. A lot of times when we think about the sources of the waves, we will reference them as isotropic sources, meaning that when the wave is emitted, it's uniform in all directions and there's no reflection or absorption of the wave as it goes from the source maybe to the receiving end, whether that's your eardrum or maybe your eye or maybe a car radio, maybe it's the car's radio signal or radio antenna in your car if you're listening to a radio wave. So again, we think about the isotropic source as being a wave that's going to be emitted uniformly in all directions. Usually we'll think about that in a spherical sense. The surface area for a sphere is going to be 4 pi r squared, and so a lot of times we'll be using the 4 pi r squared equation when we're thinking about the surface area, and we'll add that in there for our area when we're calculating for intensity. The radius being from the source to the receiving object, whatever that may be. So let's think more about the intensity. The intensity follows the inverse square law. The inverse square law is simply put, is really this concept of increasing and decreasing the radius between the point source, the source of the wave, and then the object receiving the wave. As you increase that radius, you'll see a decrease in our intensity. And as you decrease the radius, you'll see an increase in our intensity. It's an indirect relationship. And really, it goes just a little bit more than that, though, because I can actually begin to talk about how much the intensity will increase or decrease. So the intensity is going to be proportional to 1 over the radius squared. So let's think of an example. If I double the radius, what will happen to the intensity? The intensity will get weaker, of course, but more specifically, it will be 1/4 of the original intensity. If I make the radius 6 times larger, what will the intensity be? In that situation, it would be 1/36 of the original intensity. Now let's talk about two types of waves. The two types of waves that we'll be focusing on mostly in this chapter are going to be transverse waves, which are up and down waves, are the kind of the elementary definition. But the more specific definition is going to be the fact that the wave is being propagated in a perpendicular, or the wave motion is going to be perpendicular to the wave propagation. So the wave is being generated from the left and it's moving to the right. However, the motion of the wave is going up and down. So the motion of the particles are perpendicular to the direction of wave propagation. In a longitudinal wave, we consider this more of a compression wave. And so what we're seeing is we're seeing not only motion that's going to be from left to right, but also the energy transfer from left to right. And as a result, we would say that the motion of the particles in the medium is along the same line or parallel to the direction of propagation. Now, when I think about transverse waves, I think about like something like surface water, maybe seismic waves. Usually seismic waves, however, can be both. When I think about longitudinal waves, I think about sound waves and also maybe about air waves as well. Well, rather than air waves, I should say just the sound waves as they move through the air. We can also see longitudinal waves as sound waves move through water as well. I think that's a more common way to kind of consider those waves. Now, I drew the longitudinal waves in two ways, attempting to try to make it seem clear that these are kind of like compression waves. A lot of time I think about the slinky being compressed and pushed from left to right and what those longitudinal waves look like. Now, when I think about the labels that I want to put on my transverse and longitudinal waves, I think about the transverse waves having a crest at the top and a trough at the bottom of each of its waves. I also think about the longitudinal waves having compressions and rarefactions. And hopefully this is familiar from last year. We talk about those compressions being the close areas and the rarefactions being these areas that are more spread out. I always like to say that when the wave is around there, it's more rare because it's so spread out. Maybe that'll help you memorize it. Maybe it won't. Now, we talked a little bit about period and frequency today in class, and really when I'm thinking about period, what I'm thinking about is the time it takes for the wave to complete one cycle. So in this example of my transverse wave, one cycle would be all the way up and back to that point. That would be a single cycle for the wave. In this example here for a longitudinal wave, it would be this entire area right here that would represent that one cycle. Now, that measurement of that cycle is also referred to as the wavelength. One wavelength, for example, in a transverse wave, would be also representing one cycle. And we finished up this video by looking at a few of the equations that are going to be related to just basic waves and just their basic wave properties. We've talked again about equations involving, let me grab my highlighter, equations involving the frequency of a wave, which was 1 over the period. We've talked about equations involving waves measurements involving the period, which is just 1 over the frequency. But then this new concept, when not really new, I hope you kind of are familiar with this from last year, a wavelength, which is measured with the symbol lambda and has the units meters. And when we're measuring the wavelength, there's two ways that I can measure the wavelength. I can take the wavelength and I can multiply the velocity times the period, or, and that last equation's wrong, let me fix that. Or I can take the velocity and divide it by the frequency. Hopefully you made that change on your notes there. So these are my two choices for wavelength and its measurements. And that actually takes us to the end of this video and to the end of section 4 in chapter 11. So we are done for right now.